Alright, so I'm making a new video today. It's been a little while, but I have a little bit of free time, so I kind of got into starting a differential equations series. So what I've kind of been doing recently is just posting videos of questions that I like working out to help me understand them, and I'll probably continue to do that. But I want to post a couple times a week, 2 or 3 times at least, something related to differential equations and learning it kind of from start to finish. Um, and I'm sure people will benefit from that as well. So before I get too far into what this entails, this is going to be a kind of an intro. Please like and subscribe. It does help. This is the textbook that will be that I'm using as a resource. So the Fundamentals of Differential Equations, the 9th edition. It's a very good book. I like it. A lot of schools use it. If you're not using this book, I think you can still learn a lot from it. So I would encourage you to look through that. The main thing I'm using the book for is some organization in terms of what's best to learn, because I've already taken the class. So I feel it's helpful to have a book for organization purposes and learning kind of step by step, and of course for the problems. So I'm going to highlight some problems that I think are worth trying. I've already done them. I can upload solutions to them if people would like. But first, I think it's important just to talk about what it is we're doing. So let's not worry about that just yet, because you might not even be interested in it. So even though I'm using the book and I'm going to follow along with them, I'm going to kind of do stuff my own way in its own sense. So for example, we'll start by saying, what is DiffEq? Differential equations. I usually abbreviate it like this. Might be worth knowing what it is you're actually studying. And it's a branch of math that deals with equations that contain derivatives and their functions. So for example, dy dt equals 7y plus 8. Okay, so we have some function y, and we have a derivative with respect to y. So because of that, because it's an equation that contains derivatives and their functions, we say that this is a differential equation. Okay. Maybe one of the best examples of a differential equation is Newton's second law. So my channel is very I try to cover different things, but it's very much so physics related. So you'll see any example of physics, I'll probably bring it up. So F equals ma. That's probably how you saw it in your introductory physics class. Another way to think of this, though, is that acceleration is the derivative with respect to time of velocity. You could also think of it as the second derivative of x with respect to time. Okay? So Newton's second law often you can write it like this. This is often the better way of writing it, because you can find, say, the position of a particle, which is what you want to know. And somebody's at my door, so 1 second. Okay, sorry about that. So we can think as the force F being equal to mass times the second derivative of position with respect to time. So we can start with an easy case that you probably know how to solve, which is just a body in free fall. So if you drew a free body diagram, of course, you just have force due to gravity. Okay. So then we can say minus mg equals m times the second derivative of position with respect to time. The mass drops. And actually rewrite this as equal to dv dt. Okay? So minus g times dt equals dv, and we can integrate both sides. So you'll get minus gt plus, we'll call it a constant c1. So if we integrate both sides with like this, you're going to get a constant, so I'll just call c1 equals the velocity as a function of time. Okay? And then you could rewrite the velocity as simply dx dt. Multiply over the dt and integrate, and you'll get minus 1/2 gt squared plus c1t plus a new integration constant c, which is your position as a function of time. So that's kind of what I was talking about in terms of Newton's second law being a differential equation. Okay. Now these constants come from integrating this c1, which was here, this new integration constant c2. That came from the integration constant, and those are actually related to initial conditions. So we'll kind of look at that a little bit later, but those are where they're coming from. So that'll actually be coming up, not in this video, but the next video we'll talk about initial value problems. And if you know, for example, the velocity at time 0 equals 0, and the position at time 0 equals, let's say, h, well, when t is 0, we get 0 plus c1 equals your velocity at 0. Oh, so c1 is just 0. And then if we come over here, so that's plugging this into here, we can plug this into here. And again, we said c1 is 0, so we know that. If you plug in 0 into RT, you're obviously going to get 0 plus c2 equals h, and you know what your constant is now. But we're not going to worry about that too much right this second. This is more just to introduce it. So one cool thing that you can probably see is the solutions. When you solve a differential equations, you're not just going to get a number. You're not going to get 5. You're getting a function. You're solving for the function that satisfies the differential equation. So that's kind of maybe something a little bit new, but that's kind of the idea. The other thing to note is it's important to be good at calculus to be good at differential equations. You have to integrate. You obviously have to know what a derivative is, otherwise stuff probably doesn't make much sense. You have to be able to integrate often to solve. So calculus is important. I might make a calculus playlist in the future, but for right now, I take things pretty slow. I don't skip many steps, so as long as you're pretty good with it, I think it'll be fine. And then the third thing is, because of these constants, these arbitrary constants, you're not going to get a unique solution. There's a whole bunch of different things these constants could be. They're completely arbitrary. Okay? So that will be something that comes up later as well, but it's something interesting to consider. So just as you see, that's what a differential equation is. That's a start. The next thing is, why learn DiffEq? Obviously, if you're like majoring in math, it's pretty obvious why you would want to learn differential equations. You kind of have to. But why you should take this class serious and why you should study it outside of class, in my opinion, is because it's everywhere. It's used in so many different things. So if you're studying biology, we'll learn about something called a predator-prey model. Okay. That will come up. There'll be a few things relating to viruses and population growth, so populations. Whole bunch of different stuff you could apply it to. basically all of physics. So if you're studying physics, this class is an absolute must. I already showed that it's used in Newton's laws. It's used all over mechanics. It's used in circuits. It's used in electromagnetism. Used it in quantum mechanics. I'm not sure if there's a branch you don't use it in, to be honest. So you have to be good in differential equations to kind of get through physics. Chemistry. So I don't do much chemistry, but if you look at chemical reactions and rates of change, that's an example of using differential equations. Another one I don't really use, but it's in economics. It's in economics, it's in banking, it's in all sorts of different stuff. So this branch of math is just used everywhere. It's just as useful as calculus, really. So if you are interested in any science, if you're interested in any engineering, if you're interested in economics, this is all very important to know. There's obviously a lot more you can do with differential equations than what I just listed, but I think it kind of shows like, hey, if you want to know any of this stuff, it's important. Now, obviously, this is kind of what my channel does, physics. So there'll be quite a bit of physics stuff here. If you're studying physics, then that's fantastic. You'll get to see applications. If not, I think you can still learn from it. The other thing I want to do real quick is give you some definitions of what to expect. So you have something called ODEs and PDEs. ODEs are ordinary differential equations, and PDEs are partial differential equations. So what's the difference? Well, ordinary differential equations, you get functions of one variable. With PDEs, it's multivariable. And as a result, you'll get simply derivatives, ordinary derivatives. And with PDEs, you're going to get partial derivatives. Both are very important, but we're only going to focus, at least to begin with ODEs. And the book also talks a little bit about PDEs, so maybe we'll touch on it a little bit. PDEs are used in quite an extensive field as well. It's used in physics, but we'll start with ODEs. The other thing to talk about is dependent versus independent variables. So if you have y equals 3x, and we'll do it actually this way. Let's make a dependent and independent. So y equals 3x. In this case, y is the dependent variable because it depends on whatever value you use for x. Meanwhile, x is the independent variable. So you might see it dy dx equals, I'm just going to make something up, plus 2y. And I'll just put the same thing here. Okay. So you can see this y, your derivatives of y, so it's derivatives of your dependent value with respect to your independent value. Let me keep this color coordinated. This is your dependent variable y. This is your independent variable x. And these guys, these threes, are coefficients. Okay, so a lot of this stuff I'm sure you already know for the most part, just kind of taking care of that. So if I talk about dependent or independent variables, you know what I'm referring to. There's also something called order, which is simply your highest derivative. So, just as an example, if we have something like this this differential equation, we say that it is a second order differential equation because that's the highest power that you see. So we would call this second order. Okay? So when we're solving these problems, it's important to categorize different differential equations. It's important to identify what your dependent... Well, it's important to know, is this an ODE or PDE? Obviously, you're really only going to get ODEs, but generally speaking, you'd want to know the difference. Then you'd want to know is what your dependent and independent variables are. You're going to want to note the order of the derivative, or the differential equation. And then the next thing we need to talk about is linear or nonlinear. This is the last question you're going to be asking yourself. Okay? So essentially, all linear means is a linear differential equation has your dependent variable and its derivative in only first powers. Now, there is a math equation that you could think of and write it down. I think it's a little confusing. Essentially, you could think of it like, just giving you an example. This is our dependent variable, and clearly it's not linear because this is to the, trying to make that nicer, third power. So we want that to be only linear terms. Obviously, that's not really what we have. There is also a more mathy equation, which the book gives as some coefficient as a function of x, some power of a derivative plus a different coefficient as a function of x, and then another derivative one less power of the derivative plus, and then however far along you want to go, plus a 1x. So now you're all the way at the back here. Your first derivative plus a not x y, and that's equal to some function where all these coefficients are only variables of x. They don't have any y dependence. Okay? So we can go up to the top here. There's some problems that I think are worth doing to consider. And these are all famous differential equations. You can see just where they're used. Mechanics, quantum mechanics, competition between two species, electricity, heat, aerodynamics, calculus of variations, chemical reaction rate, epidemiology, economics, gas flow, aerodynamics and stress. So there's quite a bit of stuff. Anyways, so problems to maybe consider. All you have to do is say if they are linear or nonlinear, and if they're ODE or PDE, and you have to give the order. So I'll do this in, I guess, green. I would say do 1, do 2, do 5, do 9. Oh, and then we'll do 14 and 15. So these you kind of are giving a word, and you have to write the differential equation that goes along with it. So like the velocity at time t of a particle moves along a straight line. You have to model that with a differential equation. Okay? So perhaps in the next video I'll post the solutions, but for right now I'm going to go focus on my lab report.